Hello, this is Rick Powers coming to you from my home office for Western Technical College, talking about bootstrapping for basic statistics. So I'm going to share my screen here. Here's StatCrunch. And so what are we going to do with this? We're going to analyze a data set, and what we have is temperature measurement of days in February, the maximum temperature for the 28 days of February. And when we analyze data, the specific tools that we have work when we know that the population is bell-shaped. But we don't necessarily know that here. And all we have is this sample information. And so we're going to evaluate the sample to see if it seems like we can use this sample in order to think about what's true about the population. So I've already done this here. I created a box plot. And from the box plot, you can tell, well, it's skewed. And then I also did a dot plot. And from the dot plot, we see that it has outliers. There's a gap and then there's outliers. So this is telling us, because we have skewness and we have outliers, that we may not be getting good information about what the population numbers were going to be, because the sample is kind of messed up. And so there's some data points here that might not be giving us good information. And so based on the tools that we've had previously, we can't use this. So what can we do? What we can do then is we can use bootstrapping. And so then I want to show you how bootstrapping works in StatCrunch and some things about how your homework questions are worded. And then just talk about the general idea of when it looks good to use bootstrapping, when it doesn't. All right, so let's put these things away right now. And we'll talk about using StatCrunch. If we go to Applets, resampling, bootstrap a statistic. So we're going to choose our data, the max temperature for these days in February, and we're going to be bootstrapping the mean. Now down here it says seeding for random data. Seeding is a computer science term, which is how computers generate what look like random results. So when we say there's a seed, a dynamic seed means that the computer looks at like the time of day or something and says, well, let's start our calculations just by using this as like a random starting point. But if you use the fixed seed, then the computer is actually going to produce the same results every time. So on your homework, you will be required to use a fixed seed so that they can grade your homework and make sure that you're getting the right answer. For us, it doesn't matter right now because we don't need to reproduce these results or anything. So we're just going to use a dynamic seed. But on your homework, you will use the fixed seed. Now, when I click compute here, it comes up with this window. This window doesn't have anything in it right now, okay? So what are we going to do? What we're going to do is the computer is going to randomly pick out of my sample, and it's going to pick 28 times. It's going to like take them out of the hat and put them back in, and then take them out and put them back in again. So it's randomly choosing these 28 times. And so then it's going to treat those as though they were actual samples from the population. So what does this look like? Well, let's do it 1,000 times. So here we've done it 1,000 times. You see that there are these runs over here. There have been 1,000 different runs where it has done that process. And we have this thing here. Now on your homework, it's going to ask you, what is the first result? So if you go over to the left-hand side here of this little window and you see this and you pull it all the way up to the top, and then you click on the first one, it says this was the first one that we did. And it came up with this mean value of 33.55. And all of these are different. Okay, so we close that. And so it's going to ask you, what is that first number there? So that's what you're going to put in for your homework. But now you can see that this has created a kind of a bell-shaped looking thing when we did it 1,000 times. Well, let's do it a lot more times. So we're going to go up here to 10,000 or 11, doesn't matter. And it's like, wow, this looks really nice in terms of being bell-shaped. It's not exactly the same on both sides, but it looks pretty good. I could reset it and run it again for however many times I want. It's going to be different this time now because the seed was a little bit different. And so it's not exactly the same. It's not exactly symmetric, but it looks pretty nice in terms of being bell-shaped. So what we have then is these collections of samples. They all have 28 members to them. And then we found the mean and we measured it and we're getting all these different results. So this is like an estimation of what we think would happen if we'd sampled from the population. What would that look like? Well, it might look like this, okay? And so then we're saying, well, where is the actual population mean then? Well, we want the 95% confidence interval. Generally, that's what we always want. Well, this is where some people get confused. We have to open this up a little bit. We have to make this window a little bit bigger to see the whole thing. And we have, if it's 95%, then we have 2.5% to the left and 2.5% to the right. And so what we're looking at here is this number, 30.18, is on the left side. This number, 37.8, is on the right-hand side. So these are the numbers we use for the 95% confidence interval. A lot of people get confused and they think you pick this number which says 95 on it, which is not what you do. You want the 95% interval. It's two-tailed, so it has a tail of 2.5 to the left and 2.5 to the right. That means it's the 2.5th percentile here and the 97.5th percentile. Those are the numbers we use to find the 95% confidence interval for the population mean. So we think the population mean is between these two numbers, 30.18 and 37.8. So that's what bootstrapping is going to do for us. Now, could we use like the t-statistic instead of going through this bootstrapping? Well, no, we can't really, because the t-statistic is based on the assumption that we have bell-shaped data and that we have a nice sample to work with, but we don't. And so then we can't use those tools that we might have wanted to use. But bootstrapping seems to work pretty well. This looks nice. It looks pretty bell-shaped. Well, that's okay. But now we can even go beyond that. All right. We can bootstrap the standard deviation and say, well, what maybe is the standard deviation for this? And we compute that. Okay, so we do that a few thousand times. Let's go up to 10. Now this is clearly, again, not the same on both sides. It has kind of a weird shape here on the left-hand side, but it's not too bad. And so then we could say, well, the standard deviation of these things here would be, again, in this percentile between 7 and 13, basically. Now, people get confused and they say, well, what about this standard deviation here? No, this is the standard deviation of these samples, which we're not talking about here. We're talking about finding the standard deviation of the samples. That's this number down here at the bottom, which goes from 7 up to 13 or less. And so that's what we're thinking about in terms of using bootstrapping. This is now a bell-shaped distribution of results that gives us the ability to make a confidence interval. Now, we don't even do confidence intervals for standard deviations because it's really complicated. But with bootstrapping, it's not a problem. You just try it a bunch of times, see what happens, see what you get, and then you do their percentiles and you say, okay, I think it's between these two numbers. So that's nice, and you don't have any assumptions about what the underlying data, what the population might look like. Okay, so that's looking pretty good, but let's try it with something that's really weird. Okay, so let's say that I put in just some numbers here in variable 4. 4, 14, 24, and 104. Just some random digits, okay? And now we're going to do my applet, resampling, bootstrap, and I'm going to pick variable 4, and I'm going to see what happens when I do 1,000. Oh, well, that's not bell-shaped, certainly. And if I do it a lot more, it doesn't really get any better. Okay, I can do it 15,000 times and it's not going to look any different. So when we have something that the data just really doesn't work for this, we're not going to get anything that's nice in terms of being a bell-shaped distribution. Well, what if we do standard deviation? Let's try that. If we do standard deviation, compute that 1,000 times. Wow, that's weird. And then when I keep doing it over and over again, it doesn't get any better. It's just weird all the time. I can do it 10,000 times and there's no way I can say, well, where's the standard deviation? It could be anywhere. I don't know. It doesn't make sense. So bootstrapping doesn't always work. Depends on what kind of data you have to start with. But it's nice because you don't have to worry about the mathematics of what is the underlying thing going on. You just say, well, I'm just going to use the data that I have. I'm just going to make it appear like I'm sampling a bunch of different times by just randomly choosing from the sample I already have. And if it works, right, then we're pretty much okay with it. So again, a couple of things to remember when you're doing this. We'll go back to our regular one that we had. If I'm bootstrapping this February data, then if I want to know what's my first sample result, I scroll this all the way up to the top and I click on the first one. That's the one I have. And then when it asks me for the 95% confidence interval, I can't have it be like it comes up. I have to open up this window bigger and I get the 2.5th percentile, 97.5th percentile. Those are my numbers for the 95% interval there. All right. So I hope that this is helpful for you. Certainly, if you have any questions, let me know. And best wishes in doing Bootstrap.